Hello all. In the previous sessions we have seen the binary number system and conversion from one number system to the other number system, and also we have learned complements and subtraction with complements. In today's class we will be learning about Boolean algebra and logic gates. Okay, so out of this let me consider Boolean algebra first. Boolean algebra like any other mathematical system, so it is a set of elements, set of operators, okay, and so it will be consisting of number of unproved axioms or postulates. So if we consider set of elements, so any collection of objects which are having common property can be called as set of elements. So collection of objects having common property. Okay, so that can be considered as set of elements. And set of operators, so operators are the binary operator. So binary operator is an we can consider that as a rule, okay, which is applied on a pair of elements which are in the set. Okay, let us consider the set as S. So let us define the binary operator as binary operator is a rule that is applied on a pair of each pair of elements of S, so which is going to give another element, okay, which is in the same set S. So that can be considered as the operators. Okay, next we have postulates. Postulates in any mathematical system are the assumptions what we make. Those are the assumptions which will help us to derive the rules, theorems, and properties of the system. Okay. Now let us see the postulates what we have in any algebraic system. So postulates includes closure, associative, commutative, identity, next is inverse, last one is distributive. Yes, these are the 6 postulates we have. Now let us see what are these postulates one by one. So closure, a set is said to be closed, so with respect to a binary operator. So if the binary operator is applied on each pair of the set S, then if it results in an element which is a part of the set, which is an element of the set, then we say that binary operator is closed. That set is closed with respect to the binary operator. So closure, as I said, if I consider a set of natural numbers, then the operator plus is said to be closed. So because 1 plus 3, if I consider 2 elements of the set, so 1 plus 3, the result whatever we are going to get, it is also the part of the set N, or it belongs to the set N. Therefore then the binary operator plus is said to be closed with respect to the set N. So that is with respect to the closure. Next is associative law. The binary operator star is said to be associative whenever we have x star y star z which is equal to x star y star z. So whenever we have such relation, then we say the operator star is associative. Then on a set, yes. Next is commutative law. Commutative law, the binary operator star on a set S is said to be commutative if we have this relation, that is x star y is equal to y star x. If it satisfies this, then we say so it is commutative. Then identity, a set S is said to have an identity element if an element E such that x star E is equal to x, or E star x is also equal to x. Okay, yes. Next we have inverse. So inverse property says that if a set has an identity element, then there will be some element y, okay, so which will result in x star y is equal to E. So whenever we have such, okay, so relation, then we say, so y is inverse of x. Okay, now if I consider there are two operators star and dot, then the distributive law, okay, says that whenever we have, okay, the relation x star y dot z is equal to x star y dot x star z. Okay, so whenever we have such relation, then we can say that star is distributive over dot. The operators and postulates have the following meaning, in the sense plus indicates addition, next we have dot indicates multiplication, and additive inverse is subtraction, multiplicative inverse is division, okay, and so additive identity element is 0, multiplicative identity element is 1, and the only distributive law possible is dot over plus. So that is, if you have A dot B plus C, then it can be written as A into B plus A into C. Okay, so this is the meaning of these postulates. Now let us see the different theorems what we have in Boolean algebra. Now let us see the basic theorems which are used in Boolean algebra. So here I have listed the postulates as well as the theorems which we commonly use. So here in the postulates, so if you consider the Boolean, okay, algebra, in Boolean algebra we have the first, okay, postulate as closure, okay, and since the set contains only two elements and these two elements are closed with respect to the binary operator plus and dot, because when we apply, okay, plus or dot, the result whatever we are going to get 0 or 1 is 1. So this element is also a element of the same set. Therefore, so we do not consider, because by default the set is closed with respect to the binary operators plus and dot. Therefore, first postulate is not mentioned here, and second postulate what we have in the binary or Boolean algebra is identity. So here if you observe the additive identity what we have is 0, so x plus 0 is equal to x. So then the multiplicative identity what we have is 1. Okay, so this is the postulate 2 in Boolean algebra. Next is postulate 3. Postulate 3 is commutative. So commutative says x plus y is equal to y plus x. If it satisfies this, so then it is commutative, and the other version for this commutative is xy is equal to yx. Okay, and next postulate in case of Boolean algebra is distributive. So distributive is x into y plus z is equal to xy plus xz. The other version what we have is x plus yz is equal to x plus y into x plus z. Okay. Next the fifth postulate what we have is for the complement. So complement in the sense, so x plus x dash is equal to 1. So if you add the complement of a variable to the variable, then it is going to result in the identity element 1, and on the other side, so x dot x dash is equal to 0. And these are the 4 postulates we use. As I said, closure is, okay, by default the closure is applicable to the binary number system, and The last postulate what we have in case of the Boolean algebra is the elements are unique. The elements what we have in the set are unique. Since we have only two elements 0 and 1, and since 0 is not equal to 1, so the postulate 6 what we have, okay, is also satisfied by default. So these two are not considered. So only the 4 postulates we consider are 2, 3, 4 and 5. So next let us see the theorems what we have in case of Boolean algebra. So the theorem 1 says that x plus x is equal to x, and the other version what we have is x dot x is equal to x. So next theorem is x plus 1 is equal to 1 and x dot 0 is equal to 0. Third theorem is involution. So that says, so the complement of a complement is equal to the original signal. Okay, and theorem 4 is associative. So associative law, x plus y plus z, okay, can be equal to, is equal to x plus y plus z. If it satisfies this, then we say it is associative in nature. So the other version, okay, the duality of that is x into y into z is equal to xy into z. Next we have De Morgan's theorem. So De Morgan's theorem states that the complement of sum of two variables is equal to the product of individual complements. Product of individual complements. So the other version is, so the complement of a product is equal to the sum of individual complements. Okay, so that is the fifth theorem. Next is sixth theorem, which is called as absorption, and it is equal to, that is, it is given by x plus xy is equal to x. The other version is x into x plus y is equal to x. Now let us see the proof for these, okay, theorems. So if I consider theorem number 1, so theorem 1a we have x plus x is equal to x. Let us consider the LHS. LHS what we have is x plus x, okay. So let us consider this. Now let me write this as 1 into x plus x. So which is equal to, or we can write this as x plus x into 1 also. So let me write x plus x as it is, and so for this I will write x plus x dash. If you observe, so 1 can be written as x plus x dash. From postulate 5 we have, okay, therefore we can write 1 as x plus x dash. Further, so this can be combined. So if you observe, we have postulate 4b, okay, so that is distributive law. From distributive law, so it is in the expanded form. We can write the compact form of this. So that is, so x, okay, plus in place of y we have x again, in place of z we have x dash. Therefore, so this further can be written as x plus, so x into x dash. If you, okay, look into the table, x into x dash is available here. It is equal to 0, and x plus 0 is nothing but x. So from the postulates, by taking the reference or with the aid of the postulates, we can prove that x plus x is equal to x. So this is for the theorem 1. So if you consider the part B of the theorem 1, so in theorem 1 we have part B as x into x is equal to x. Similar to this we can prove. So let us consider x into x, okay. So let me consider x into x plus 0, okay, because we know that, so variable or 0 will result in the same variable. Therefore x dot x is equal to x dot x plus 0 is equal to x dot x. Now for this 0 I will write x into x dash. Now let us, okay, so consider the postulate 4. So we have xy plus xz format here, xy plus xz, so which can be written as x, okay, into y plus z. So whereas x plus x dash, where we have x plus x dash, yes, so here we have x plus x dash is equal to 1. Therefore this becomes x dot 1, which is equal to x. Therefore, so it is proved that the theorem 1 what we have, so is proved. So we can say x plus x is equal to x and x dot x is equal to x. So this is the proof for theorem 1. Now let us consider theorem 2. Theorem 2 is x plus 1 is equal to 1. Let me consider the LHS. So this can be written as x plus 1 into 1. Further, this can be written as x plus x dash from postulate 5, and so now it is in the expanded form. So using postulate 4b, we can write this as x plus 1 dot x dash. So which is nothing but x plus x dash. So x plus x dash from postulate 5a, it is 1. Therefore x plus 1 is equal to 1. By duality, the part B of theorem 2 can be written as x dot 0 is equal to 0. So in duality, what do? We replace 1 by 0 and plus by dot, and vice versa. Okay. So by duality we can write the part B of theorem 2. Now if you consider the involution, that is complement of symbol, then so it can be written like this. So if I consider x, okay, x dash, further x dash of, okay, dash, that is complement of a complement. So x, let us assume it is 0 1, okay, x dash will be 1 0. So complement of this will be 1 0. So therefore x dash of whole dash is equal to x. So this is for the theorem 3. Next we have associative. So in associative we have x plus of y plus z, which is equal to x plus y, okay, plus z. So let me consider 3 variables for that. So let me consider x, okay, x plus y and y plus z. Later let me consider x plus y plus z, and last y, x plus y plus z. Okay, let me consider x plus y plus z. So let me, okay, write the values for this. Okay, the possible combinations are 0 0 0 to 1 1 1. Now x or y is 0 0 1 1 1 1 1 1. Y or z is 0 1 1 1 0 1 1 1. Now x, okay, plus yz, x plus yz, x or, okay, yz, if I consider. So first column entry is 0 1 1 1, okay. Next after 4 entries, so we have 0 or 1, so 1 1 1 1, and the last one x plus y plus z, okay, 0 0 first, okay, 0 or 0. Next we have 1 or 0 is 1, 1 or 0 is 1, 1 1, 1 or 1 is 1, 1 or 0 is 1, 1 1 1. So if you check the last 2 column entries, so we have, so which are equal. Therefore, so we can say that this is the proof for associative law. Okay. So we have seen the proof for the 4 theorems. Now let us consider the De Morgan theorem. So De Morgan theorem, we have considered this for 2 variables here. So let us consider 2 variables, and let us, okay, consider the first part of it. So similar associative law, I have shown only the proof for the part A. Part B can also be proved in the same way. Now let me consider. So first De Morgan's theorem, x plus, okay, yes. So now let us consider the possible combinations. Complement of x 1 1 0 0, complement of y 1 0 1 0, x or y is 0 triple 1, x or y complement is 1 triple 0. Okay. Next we have add between these two, 1 and 1 is 1, all other combinations we will get 0. Therefore, the part A of the De Morgan's theorem is proved. Okay. Next, if you consider the part B, okay, so what do we have? We have xy, then we have xy whole dash, then we have x dash plus y dash. Let me consider 0, 0, 0, 1, 1, 0, 1, 1. Next, complement of x and complement of y, x into y 0, okay, since it is an AND operation. So, we get 0 for all except for the last combination. Next, we have xy dash is complement of this. So, we get 1, 1, 0, and last one is OR between these two. OR between these two is 1, 1, 1, 0. Okay, this is the proof for De Morgan's theorem. Okay, now let us consider the last theorem, theorem 6. Okay, in this also we have two parts. So, first one is theorem 6a. So, which okay, we have as x plus xy is equal to x. X plus xy is equal to x. Let us consider LHS. So, in this, so we have this can be written as, if you consider okay the distributive law, this can be written as x plus x let us consider LHS. So, in this we can take out x as common and we will get 1 plus y. So, further 1 plus y, so 1 plus any variable will result in 1. So, this can be written as x. If you consider part B, this is part A, 6 part, okay, 6 A, and now let us consider 6B, x plus xy, so is equal to x. So, in this we can write this as x plus xy again. So, if I multiply, then this can be further written as, because x into x, so x into x is x, okay, xy will, now if I take out x as common, 1 plus y is 1, so this can also be written as x. So, these are the proof for the theorems what we use in Boolean algebra. So, this is about the Boolean algebra, the postulates what we have in Boolean algebra, and theorems what we use in Boolean algebra. Okay. In the next class we will be learning about the logic gates, different logic operations. Thank you.